portion of that expression.
Mm-hmm.
There was a
It
problem,
should
I
be
think.
okay. So it should be del f del y minus
Minus
dx
ddx.
dx of
Yes.
del f del y prime. Yeah, you are correct.
Yes.
Okay. Uh, so let's take an example of a spring. Okay. So imagine uh, this is the fixed end and this is the spring, and its spring constant is k, and you are applying a force F at the other end, the free end, and that causes an elongation of, let's say, u. Okay, so you all know the relation should be F equals k times u. Okay, now now this we already know. Okay, let's say from the free body diagram of the spring and so on. But let's say if I define define a quantity called strain energy. Okay, actually strain energy is quite well defined quantity, and you must be familiar with the expression for that. Can you tell me what should be the expression for strain energy?
half of k x u square.
Half ku squared. Okay, it basically represents the amount of work done to cause, since it's a linear spring, so if the y-axis represents F and the x-axis represents the displacement, so it can be represented by a straight line with a slope of k. Okay, and at any u, the strain energy that we are talking about is basically the amount of work done on the spring. And since the spring is an elastic element, we expect to receive the same amount of energy while we will be unloading the spring. Okay, that means while the spring is stretched, it can do the same amount of work, okay, on another body. Okay, so we are expecting to get back this much of energy, hence it is called a strain energy. But I'll define another quantity called the work potential. Work potential. Okay, now I'll define this quantity to be F times U. Okay, which basically represents this whole area. Now, to be frank, this expression Fu is just for mathematical interest. Okay, but if you do emphasize on the the name of the term that it defines, which is called the work potential. That means up until you have applied this much of force F. If this is the amount of force you could apply, the source that it is which is applying this force had the work potential, okay, to cause this much of work. So if the source could move an object by a distance of u and apply a force, a maximum force of F, this is the maximum work the source could have done, okay, on any object. For example, let's say there is a frictional surface, there is a block, okay, you're applying a force of F. So the source is applying a force of F, and it could move the object, okay, by applying this much of force to a distance of u. So then it would be doing a total work of Fu, okay, which is the work potential. Now with these two, I'll define a third quantity. Okay. And I'll call it the potential energy. Okay. Which is defined as the strain energy minus the work potential. Okay. The strain energy minus the work potential. So the final expression for this quantity is half Ku squared minus Fu. Okay. So now, what is the significance of this term, this potential energy? We will see if I would like to minimize this work potential with respect to U, the displacement of the free end of the spring, then the conditions are that, actually in this case it would not be a partial derivative. D pi du is 0. And the second derivative should be greater than 0. That we would check, but this should be equal to 0. Now if we do that, then you would see Ku minus F equals 0, or in other words, Ku equals F. That means, you see, this force was applied by the external source on a spring with a stiffness of K. And this is the response of the spring. That means on application of this force, this the free end of the spring displaces by a distance of U. That is the response of the spring. So response is such that it minimizes this so-called potential energy, which is the strain energy minus the work potential. Okay. Now, what is the significance of this thing? Because now we will extend this to, see, first of all, a spring is a part of a lumped system. Okay. Lumped systems are like this. There would be a mass, there would be a spring, there would be a damper, and a combination of one or more of these. Okay. Now, why do we call these as the lump system? You see, when you have a structure, let's say a building, okay, which would be oscillating under, let's say, when there is an earthquake. Okay, let's say the building is, oscillating when there is an earthquake. So that is the real object. Okay, where the mass is distributed everywhere, where the stiffness is distributed everywhere, where the damping is distributed everywhere. But we simplify the structure, simplify the model, okay, by taking a series of these are called single. This is a 1 DOF spring mass damper system. So what do? We do multi-degree of freedom such systems. Okay. If you do consider the the building material is continuum, okay, then ideally there should be infinite number of degrees of freedom. Okay, and ideally you can accurately model the oscillation of the building by taking infinite number of such lump systems. Okay, but see, by taking a limited number of such lump systems, like I can model each floor with a mass, okay, and then each on each floor, whatever the support is, there is the columns and the beams, I can model them with the help of springs and the dampers, and I can keep on doing this for multiple floors. Okay, So this is an approximation with a limited number of degree of freedom. Okay, and this approximation can give you pretty accurate result. Okay, in different circumstances. Okay, now you can also contest this term continuum. We have been repeating this term since the last class. Is the building material really continuum? No, it's not. You see, the building material, you can think of the bricks, you can think of the metal in them. Okay, like the steel rods that are there. So all of these are made of grains, and grains have grain boundaries, hence the discontinuities are there. Okay, so obviously it's not a continuum. It's not just a smooth distribution of matter. Okay, it's not a smudge. There are discrete, grains. And even if you look into the grains, these grains are essentially single crystals which are made of atoms. Okay, and by now we already know that even the atoms are not fundamental particles. But you see, all of this is not required when you are studying the macroscopic mechanical behavior of a structure. Okay, you can simplify the model. You can simplify to be for it to be a continuum, and that's where FEM plays a role. But you can even simplify that to be as a system of as a complex version of lumped systems. Okay, so so here we are discussing about an element from a lumped system. So if this is a lumped system, spring or the stiffness is one of the elements in the lumped system. Okay, but why is this exercise important for us when we are trying to learn material behavior, or sorry, not material behavior, the structural behavior for a continuum? You see, we are ready with our the differential equation generator. Okay, you can think of Euler Lagrange equation to be the method, general method for finding the differential equation. Okay, which you can then solve to find out the solution. Okay, so obviously we are talking about a domain where we can take derivatives of. Okay, so therefore we are discussing continuum. Okay, so what we'll do now, we'll extend this idea that you can get the the governing equilibrium equation. This is not a differential equation, it's an algebraic equation. Like we discussed in the last class, when you have a function, let's say strain energy or work potential, or for that matter potential energy, all of these are functions of u, and when you minimize them, you get an algebraic equation, and from that you get a value for this quantity u. Okay, so this is an algebraic equation, but it is equilibrium equation. Okay, and for this course of finite element method, we will restrict ourselves within the domains of equilibrium, and let's see how we can use the same principle to get the equilibrium equation for a continuum. Obviously, that equation is going to be a differential equation, and since it is going to be a differential equation, okay, then it should be originating from not a function but a functional. Okay, so we'll try to find out that functional. Okay, so okay, so today we can take this example of a one-dimensional bar. Okay, and this type of bar you have not seen so far. So there is a slender member which we can treat it as a bar, but so far you have seen the bar being only pulled at the end. Okay, let's say by this end load P. Okay, so this end is the fixed end. Here U is 0. Okay, U again here is defined as a displacement, but you see this time U is not a free parameter. Okay, U is a function of X. Now what is X? X is the coordinate along the bar. Okay, and the length of the bar is L. The area of cross section is A, and the Young's modulus of the bar is E. Okay, pretty standard. Now there is one new thing that you are not familiar with, which is a distributed load on an axial bar. Okay. We'll call this Q of X, and by that we are leaving the opportunity. We are, not leaving the opportunity. We are, we are allowing Q to be a function of X. So the distributed load need not be uniform, and for that matter, it should not be everywhere within the bar. It can be only at a very restricted segment, which means for the rest of it, it is 0. Okay, now now let's say if I take a small differential element, okay, of length dx at a distance x away from the fixed end, okay, and draw the free body diagram for the same. So this one has a dimension of dx, okay, and this one has a distributed load qx, and you might recall this distributed load is essentially force per unit length. Okay, now if I look at the stress on either side, let's say on this side it is sigma x, on the other side it is going to be sigma x plus d sigma x dx dx. Okay, এই অবধি বোঝা গেল?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Now it is time to write the equations of equilibrium. Now obviously we are considering a case where all of these distributed and concentrated forces are small enough for the bar not to be detached from the fixed end, which means the bar is not going anywhere, which means the bar has to be in equilibrium under the application of those forces. Obviously there would be some support reaction, but I'm not going there right now. So if I sum all the forces in x direction, that should be equal to 0 in order for the equilibrium to happen. Now if I look at this, then on the right hand side the positive force is a times sigma x plus d sigma x dx. By this time we would refer to any quantity, let's say w is any random quantity, so dw dx as W prime. So with that, we'd call it sigma x prime. Okay. Dx. So that is the force in the right hand side. In the left hand side, the force is sigma x times A. So hence minus sigma x. Plus this force due to the distributed load, which is qx dx. That is a net force in x direction on this differential element. And that goes to 0. Do you find anything wrong in this one?
No, sir.
No, sir.
Okay. What about the point load? Should we not consider that?
The point load
Yes,
is
sir.
this
Yes, sir. P will be considered.
point load.
Should we consider the point load in addition? Do you think the point load should be considered in addition to whatever has been considered so far?
No, sir. It is a differential element, so P will not be considered, I think.
Exactly. Actually, that force P, okay, is actually being considered. When I'm considering the stress on this side, it is actually being considered. And similarly, that force is also considered on this side when I'm considering the stress on this side. Okay. So at this point, I'll not be bothering myself. Okay. What happens to the point load within the bar? But when it comes to the boundary condition, we'll definitely bother ourselves with that. So we'll go there. Okay. So therefore, we have these two terms cancelled out. Okay. And eventually, our differential equation would look something like this. A times sigma x prime plus q of x equals 0. Okay. But then our differential equation should be in terms of u. Okay. And here we have the differential equation in terms of sigma x. So we'll have to convert that as well. Okay. So sigma x, I guess this part should be pretty simple, is Young's modulus times the strain in x direction. But the strain in x direction is actually du dx. You see, even during our undergrad studies, we have learned that strain is change in length per unit length, which is a pretty vague definition of it. That means I should be taking the total length L, okay, and then the total change U at this end, and then divide U. So at this free end, let's say the UL is the maximum displacement, and then this UL by L is a strain. But that is a strain where? That actually represents the average strain over the entire bar. But strain, and for that matter stress, is not going to be constant everywhere. For example, if I drop this P term from here, I mean, in presence of a distributed load, the stresses and the strain are not going to be constant along the length. For example, if I drop this P term, there would obviously be some amount of elongation because of this distributed load, which would mean there would be obviously some amount of strain. Okay, but since at the free end there is no force, the layer immediately behind that free end, there would be no stress. The stress would be 0. By the definition of stress, the stress has to be 0. Okay, But how can the stress be zero if there is a non-zero strain? The answer is the strain is actually zero at the free end. Okay, if there is no concentrated force. Okay, it's just that it is not zero everywhere. Actually, in absence of P and even in presence of P, the strain is highest at the fixed end. Okay, and then it gradually reduces depending on the profile of the distributed load. Okay, if there is no distributed load, if there is only a concentrated force, then everywhere the stress is the same. Wherever you take the free body diagram is just P versus P on either side. So stress is the same. Okay, which would mean the strain is also the same. But if it has a distributed load, the strain is not going to be same, and hence strain requires a differential definition. Okay, which means I can only define strain within a differential element. For example, up to this is x, and let's say up to this the displacement is u. This element is dx, but at this end the displacement is u plus du dx times dx on this differential element. But then what is the change in length of this differential element? Both of these faces of the differential element are displaced by u, but on the right hand side it is additionally displaced by this amount. So the strain is going to be du dx dx divided by dx. This is the strain, which is u prime, and from this এই অবধি বোঝা গেল কি u prime কেন হবে strain?
Yes, sir.
Okay, is it something new or you were familiar with this definition?
Sir, somewhat familiar. I have learned. I have seen it in the solid mechanics, that supplementary that you have sent.
Okay, means you have not seen it in undergrads.
Somewhat similar, not similar, not means accurately.
Okay. So u prime, okay, which would mean that this differential equation becomes EA u double prime. I'm considering that neither the Young's modulus is changing along the bar. That means the bar is made of homogeneous material, and also the cross section is not changing. That means there is no taper on the bar. These two assumptions I'm making. Otherwise, the definition would, the expression should look a little different. It would be something like this: EA u prime whole prime. That means you take derivative of u, multiply with e and a, okay, and then for the whole quantity take a derivative. But that basically means e a u double prime, okay, when everything else is constant, plus q of x equals 0, and that is the differential equation or the equilibrium equation for one-dimensional bar. But there are boundary conditions. Okay, what are they? u0 is 0. So u is 0 only on the left hand side. On the right hand side, u is non-zero. Okay, or for that matter, you do not know u beforehand. The value of u depends on what is the distributed force and what is the concentrated force. Okay, it is not known beforehand. Okay, so this type of boundary condition is called Dirichlet boundary condition, when the boundary condition is directly on the degree of freedom. Okay, and on the right hand side you have this boundary condition: sigma x at L is P by A. Okay, which means u prime at L is P by EA. So the second boundary condition on the right hand side is on the normal derivative. That means normal to this face is x. So with respect to the normal derivative of u, okay. So on the left hand side, the boundary condition is directly on u. On the right hand side, it is on the normal derivative. This type of boundary conditions are called Newman, couple of n's here, boundary condition. Okay.
স্যার আরেকবার বলে বুঝতে পারিনি।
কোন পার্টটা বুঝতে পারোনি?
নিউম্যান
ওটা একটা নাম, ওটা একটা শুধু নাম, ঠিক আছে, মানে একজন সায়েন্টিস্টের নাম। So Dirichlet boundary condition is directly on the degree of freedom, and Neumann boundary condition is actually a traction boundary condition. Okay, মানে whatever is the traction on the free end. Now what is traction? That has been discussed in that solid mechanics notes, and I'll discuss it in even further detail when we do a dedicated class for solid mechanics. Okay, but for the time being, just accept there is Dirichlet boundary condition, there is Neumann boundary condition. There would be boundary conditions where the displacement must be specified, and there would be boundary conditions where the forces are specified. Okay, actually, even if there was no forces specified, that means even if I had not drawn this arrow, okay, and written this P, that would have also been okay. Okay, but in order to solve an equilibrium problem, I need to have one of the sides to be fixed, at least one of the sides. If I fix both the sides, then it becomes a statically indeterminate problem. And in our strength of materials course, solid mechanics course, we have learned to solve the statically indeterminate problems in a much different way than statically determinate problems. For statically determinate problems, we would initially solve the entire equilibrium equation and determine all the forces, all the moments, and then we would calculate the stresses and the strains and the displacements. Okay, that's the flow: forces, stresses, strains, and displacements. When we are dealing with statically indeterminate sort of problems, okay, so we'll have to write down all the equations, all the equilibrium equations, but then we cannot solve them because the problem is statically indeterminate, which means literally that you cannot solve it from the equilibrium equation. And then we would write all the expressions for stresses, strains, and displacement, and then all of these equations will have to solve simultaneously, sort of a huge set of linear equations we'll have to solve simultaneously. That's how we solved statically indeterminate problems. But fun thing is, when you use the numerical method such as finite element method, irrespective of the problem's nature, that is being statically indeterminate or statically determinate, you will use exactly the same method to solve the problem. Okay, so in the coming classes we will learn how to do that. Achha. So this differential equation along with this boundary condition forms something called a strong form. What is the strong form? We'll come to this later. Why is it a strong form? We'll come to this even later. Okay. Now keep this thing in mind. Okay. And then let me delete all the steps that we did to get the equilibrium equation. Let us see if we have any other way to arrive at this differential equation. Okay, where we don't have to draw this free body diagram. What is the purpose of free body diagram? Writing an equilibrium equation. Let's say we don't have to do that. Now we already know the expression for the strain, and now I'm dropping the the suffix x, okay, because there is only one component of strain here. So epsilon being u prime, okay. Although I'm calling it epsilon, when you use LaTeX or Word equation editor, you should use the var epsilon. Okay, a backslash var epsilon space would give you this expression. Anyways, so if that is the expression for strain, then the expression for what should be the expression for strain energy? Can anyone tell me?
Half epsilon square by E.
Epsilon squared by E,
So half into sigma into epsilon
half
into
into
volume.
sigma into epsilon. Okay. So it's basically compared with the spring diagram, stress, strain, Hooke's law, slope, Young's modulus. You are at certain strain. So this is what is strain energy. Okay, and that is what you are supposed to get back when you release the bar, and if you attach if let's say it is a vertical bar, and if you attach a weight, you would be able to pull it vertically and do this much amount of work on that weight. Okay, so how much is this? As you pointed out, that is sigma times epsilon. That is also actually sigma times epsilon by 2. That is also half E times epsilon squared. You see, E times epsilon is sigma, and epsilon further will give you this squared area. Then half of that is this triangle, hence the half. But you see, this is not the strain energy. This quantity is strain energy density. You see, stress is not force, but force by unit area. And strain is not displacement, it is displacement per unit length. Okay, I'm just showing the dimensions here. Don't just, I'm just contradicting myself by writing U by L, but I'm just comparing dimensions here. So the strain energy that you're seeing here, it is per unit volume. You see, area times length is the volume. So this quantity is strain energy density. So I must integrate this with A times dx, and that's what is going to be my strain energy. Is it clear now?
Yes, sir.
Yes, sir.
Okay, so this expression would look like half comes out of the integration, okay, because it's not a function of x. E and A could be functions of x. Okay, so for the timing I'm leaving it there, but then later I'll assume that they are constants. U prime squared dx, that is the strain energy. Okay, and work potential is going to be two quantities. First of all, P times U at L. Okay, P times U at L. So whatever is the displacement of the free end, that I'm multiplying with P. Okay, so whatever is the source of P, that could have done at most this much of work. Okay, and for the distributed load, we have no choice but to integrate Qx dx is the differential force dF, but times U. Qx times dx is the differential force dF, okay, times U is the displacement due to that differential. I mean, it's not the displacement due to that, but since the source is able to move by a distance of U, that means the distributed load could have caused this much of work done at most. Okay, so now if I delete this diagram, I don't need it any further, that's why I delete it or erase it, and then then I have this expression for the potential energy. I'm just trying to do one-on-one analogy with the spring example. Okay. So it is strain energy minus work potential. So it is 1/2 0 to L EA U prime squared dx minus P U times L plus 0 to L U of x qx dx. Not plus, it's actually minus. Okay. So for the spring case, we just took derivative, or rather we minimized this potential energy with respect to the displacement. But this displacement of the free end of the spring was just a single number. Okay. But right now we are looking at u, which is a function of x. That means the different locations within the bar are deforming by different amounts. Okay, which is obvious because the fixed end is not deforming at all. It's not moving at all, but the free end is moving somewhere. So here we are looking for u as a function of x. We want to find out that functional form. Now, what sort of equation gives us the functional form? Obviously, a differential equation. Okay, and how do we arrive at that differential equation? We need to minimize the potential energy. Okay, so we need to minimize pi with respect to u and u prime. Now, does this expression look familiar? All I'm saying is, does this operation of minimization of a definite integral look familiar?
Yes, sir.
It is actually minimization of a functional. You see, I don't know how many of you recall delta function, Dirac delta function. We probably discussed about that in the last week's class. Okay. So obviously these two I can easily incorporate in a single integration, u times q. I'm not showing as a function of x, but it is implied. Okay. But for this one, I can show it to be, see, p is a constant, and this one I can show it to be 0 to L delta x minus L dx. Okay. So ul can be written like this: u as a function of x, delta x minus L dx. So minus p u Dirac delta function x minus L dx. Okay, that's what is the functional, and that basically is your f. This quantity is your f. Okay. So what we should be doing is, we can directly try to write the Euler Lagrange equation. Okay, and we'll face some problems. Okay, for example, with this part of the term will not be able to treat the same way for the remaining terms. Okay, it's because this one comes from a boundary condition, and it's not actually a part of a differential equation. Okay, you see, when we wrote this differential equation, nowhere p became a part of it. Okay, and that's why we cannot use this one, okay, which is essentially a boundary condition, be a part of the integral. Okay, if you recall, even for the derivation of Euler Lagrange equation, the example we took, okay, that y value at x1 was given as y1, y value at x2 was given as y2, which means on both the ends there was Dirichlet boundary conditions. Okay, which is different from this example. In this example, on one side there is a Dirichlet boundary condition, on the other side there is a Neumann boundary condition. And that's why it is important to show there is, irrespective of the boundary condition, okay, the differential equation remains the same. The differential equation doesn't change because of the boundary condition. That means instead of applying p, if I had applied twice p or 0p, okay, the differential equation would still remain the same. Okay, so in order to optimize this quantity, okay, what you do is you do a little treatment where you'd write the first variation of pi, okay, directly from this expression. Okay, so basically I'm leaving it as p times u at L. Okay, now the first variation of pi is where I take derivative of everything with respect to u and u prime. Okay, so the first term would look, like the way we wrote the first variation for the functional. You can try it on your own. So this is what it is going to look like. EA, you see, if I take the derivative of this thing with respect to u prime, it is going to be, so you can imagine, if I consider this to be f, EA half EA u prime squared, okay, and then if I take derivative with respect to u prime, so it is going to be half would be multiplied with 2, so it is going to be twice EA u prime multiplying half, so EA u prime, and then I need to multiply with the variation of u prime, okay, times dx. Okay, actually I'll use the symbol v as the variation of u, not the variation, and arbitrary variation of u. And because v is a variation of u, v is 0 in gamma u. That means wherever the value of u is given. That implies v is 0 at x equals 0. V is 0 at x equals 0 not because u is 0 at x equals 0. V is 0 at x equals 0 because the value of u at x equals 0 is given. Even if this value was 10, okay, the value of v should be 0. Okay. So the first variation of pi, okay, that I'm trying to write here. So this is for the first term. For the third term, it would be, see, this part is not a function of u prime, the explicit function of u prime, but a direct function of u. So it is going to be q times v dx, and this one would be v prime. Okay. For the last one, it is going to be simply, let's say if I take derivative of u with respect to u, it is going to be u, right? It is going to be 1, right? So 1 times v at x equal L. So this is what the expression would look like. Okay. And if you are confused how I got this expression, this expression from the other one, imagine writing it like this: p times u of x times delta of x minus L. Then see, delta of x minus L is not a function of u or u prime, but u is, okay, so when you take the first variation, so this term would be v, okay, first variation, so this term would be replaced with v, and therefore in the end it would result into p times v of L. Okay, that's how the Dirac delta function works, and this should be true for all v. And this sentence or this statement is, you know, extremely necessary. Without this, okay, this whole exercise has no meaning. You being able to say this means that you can go back from this statement to the upper statement. Okay, the arbitrariness of v, okay, is mandatory. Otherwise you are going through loss of information. Okay, you are not stating the whole truth. So when I write it like this, for the first term I can do integration by parts, and I'll try to bring the derivative from v to u. So the first term would be ea u prime v at L minus ea u prime v at 0 minus 0 to L ea u double prime v, not v, eau double prime plus q times v dx, okay, minus p times v, and this first variation must go to 0. In order for you to be able to minimize this potential energy, the first variation must go to 0. And if indeed that first variation goes to 0, now I don't need the derivation of the spring system. Okay, so if I look at these two expressions, okay, what is the value of ea u prime v at x equals 0? Can anybody tell this?
It's a 0.
Why?
Sir, because it is an arbitrary variation and the boundary condition is v0 equals to 0. V at 0 equals to 0.
V at 0 is 0. But why is V 0 at x equals 0?
Because V is an arbitrary variation of U. In the previous problem, when we take delta y is an arbitrary variation of yx, then we took in order to V be an arbitrary variation, it should be satisfy a boundary condition, that is V 0 equals to 0.
Okay. Let me finish. It's not because of the arbitrariness of V. Of course, you are going to use the arbitrariness of V in just within another minute. But the reason V is 0 is, you see, what was the meaning of variation again? Let's say at one location, one of the locations, value of U is given. Okay. And beyond that, U could be anything. Okay. Let's say this is the actual solution of U. Okay. Now that an arbitrary function would be admissible for a potential solution to that minimization problem. Okay, please listen to this sentence very carefully. That an arbitrary function, again, U tilde, not this one is not U tilde, this one is U. This one is U tilde. That an arbitrary function U tilde would be admissible, okay, for a potential solution to this minimization problem, okay, requires it to satisfy the boundary condition. The boundary condition which are of Dirichlet type. The boundary condition which is directly on U, that must be satisfied. Now, what was V again? The variation was the function lying in between. The actual solution, the actual function that minimizes the functional or the definite integral, okay, and a potential candidate for solution. Okay, the difference between the two was the variation V. Okay, actually this was epsilon times V, whatever the case may be, which means wherever the value of U is actually given, this V automatically has to be 0. V is 0 at x equals 0 because U at 0 is specified, not because U at 0 is 0, because U at 0 has been mentioned. I cannot make the same assumption about x equal L. Unlike the previous example, like the Brachistochrone problem, I cannot say the variation at either end is 0. No, it's not. On the other end, V can also be 0, but V is arbitrary. It can be 0, it may not be 0. But then how do you look at this expression? If this is not 0, in general, the term in general means always, okay, for any arbitrary V. This is not true for any arbitrary V. V being an arbitrary function of x, it's not true all the time. So how do you look at this expression? You see, the boundary condition is actually, how do we do is we club these two boundary terms, okay, which tells us, eventually this tells us that the first variation of pi is E A U prime minus P, this quantity evaluated at L, multiplying V at L, okay, which is this term minus this term, minus 0 to L E A U double prime plus Q V dx equals 0, and this is true for all V, all admissible V. Okay. Now, this would mean this, now you are going to use the arbitrariness. And by this arbitrariness, you would say that this integrand is also 0 because V is arbitrary, and this boundary condition is also 0. Okay, so at the beginning of this problem, okay, this minimization problem, we are only given the Dirichlet boundary condition. As an output to this minimization problem, will give you the differential equation, which is indeed the Euler Lagrange equation. Okay, and this is true for anywhere between 0 to L. And also this boundary condition, the Neumann boundary condition, would also be the output of the minimization of the functional. So boundary conditions would be, now these two can be obtained using the arbitrariness of V. Okay, I mean, I can set V to be 0 anywhere between 0 to L except for x equal L. Okay, which would make this boundary condition equal 0. Okay, and I can also make V to be a Dirac delta function anywhere between 0 and L. That means the value of this quantity should be 0 at that value of x. Now that value of x is also arbitrary, hence this has to be 0 everywhere between 0 to L. Boundary conditions are one that was initially given to us. The other one is that E A U prime at x equal L is P. So we are getting through minimization, okay, we are getting the same differential equation that we had obtained from the equilibrium, I mean from the free body diagram and the equilibrium equation. Okay, so what we have learned today, that we can use Euler Lagrange equation, okay, to get the equilibrium equation in a differential form, okay, for a continuum, okay, from the potential energy, which is basically strain energy minus the work potential. Okay, so we can minimize that functional and we will be getting the governing differential equation of the system. Okay, so is this part clear to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Okay. Today I'll give you some assignments which are not related to this one. Okay. But next day onwards, we would be picking up from here only. Okay. So, so first of all, this expression, this statement, where we write the potential energy that we are supposed to minimize, we'd call that M statement or the minimization statement. The first variation of pi for us is the V statement or the variational statement. Okay, and then there is the strong form. This V statement and the M statement, these are the weak forms, both of them. Okay, both of them are weak forms, and the differential equation is a strong form. Okay, today we have learned, actually day before and today we have learned how to go from any of the weak forms to the strong form. Okay, and we have also mentioned that this is a two-way travel. If I can write this expression and mention the arbitrariness of V, then from this expression also I can go back above. Same goes over here. Okay, In the next class, we will see how we can go from the strong form to the weak form. And the key to finite element method is to go from a given strong form to a weak form. Okay. So far, we have learned how to go from a weak form to a strong form, which is the differential equation, basically Euler Lagrange equation. Now, given the Euler Lagrange equation of a system, how do we go to a weak form is what we would learn in the next class. And with that, we will be one step ahead in the direction of finite element method. Okay. So today I'm going to give you assignments which are actually mentioned in the notes. Okay. And which are not very related to whatever we have discussed so far, but I'm still going to give you those because you need to make yourselves familiar with the variational formulation. Okay. So there will be two more problems discussed. Okay. So we have solved, we have, got the Euler Lagrange equation. Actually, we didn't even get the Euler Lagrange equation for brachistochrone problem. Okay. I'll mention two more problems. Geodesic problem. Okay. And actually, I should have written the other one before this one, which is isoperimetric problem. Okay. These three are assignments for you today. So you need to write. By write, I mean you need to derive. Okay. Just simply don't write the expression in a single line. You need to derive. You need to arrive at the expression. The problem statement, that means in the functional form, okay, in a mathematical form, problem statement and solution. That means first write the problem statement in the form of functional, then write the Euler Lagrange equation, and then solve the differential equation. For each of these three, okay, the brachistochrone problem, the isoperimetric problem, and the geodesic problem. Brachistochrone problem is an unconstrained minimization problem. Isoperimetric problem uses a global constraint. Okay, and geodesic problem uses localized or local constraint. Okay, once you go through each of these, okay, you'll know what is meant by a global or a local constraint. And I'm also not giving away the what is the meaning of geodesic and isoperimetric problem. For that, you can go through my notes. Okay, I think there is quite a bit of detail in there. Okay, if you do not find sufficient detail, you should find you should go to, I have mentioned this one earlier, hyphen.com, and find Professor Chandrasekhar Joge's class note on finite element method, okay, which you can think of as a superset of my class note. And there, I guess you'll find all of this. Okay, I need you to go and study them, understand them. If you have a doubt, ask me. Okay, and these two parts, right, deriving the problem statement in the functional form, where you understand each and every term, meaning of each and every term, and explain why the particular problem has a particular functional form. And then there will be different steps of solution. The first step is to get the Euler Lagrange equation, and so on. So all of this is what I need you to do on a fair copy. Okay, neat and clean, like you are writing a report or a thesis or a like an exam paper. It should be very neatly done. Okay, and you need to maintain that copy throughout the semester. Okay, and if there is no instruction from the institute, that is what I'll be evaluating. Okay, that assignment copy is what I'll be evaluating. So so take this as an assignment. Okay, and this would be your assignment until we meet in the next time. Okay, if you have any further question, let me know. If you don't, then we can stop the class.
স্যার ওখানে ইউটেলটা আর ইউ এর জায়গায় ইউটেলটা ধরে ওটা কেমন ভাবে করলো একটু বুঝলাম না, বুঝছিলাম না। মানে এর আগের দিনও করা হয়েছিল যে প্রথমে আলাদা লাগলেন ইকুয়েশনের সময়
ওখানে যেটা করা হলো
স্কেলিং ফ্যাক্টর আনা হয়, ডেল ওয়াই ধরা হয় প্রথমে।
হ্যাঁ, লেট মি টেল ইউ একটা জিনিস বলি। ধরো একটা এই ফাংশনালটা, this is f of y prime dx integrated between 0 to L. Okay, and that needs to be minimized with respect to y and y prime. And let's say y is the function that minimizes it. Okay, and y tilde is a different function which doesn't minimize this. But let's say y equals sine x minimizes this, but y tilde is cos x, which doesn't minimize this. Okay, but it will give you some value of y. Okay, but then let's say at this end the value of y is given, and this is that unknown solution that you are looking for. You don't know that. You are, you know, eventually you'll get the Euler Lagrange equation, and that you will solve to get the actual function. Okay, for example, in Brachistochrone problem, some of you said that intuitionally it looks like a straight line between the 2 points is going to give me the least time. It gives you least distance, it doesn't give you least time. Okay, the actual solution is, if the chute is, you know, frictionless, that needs to be mentioned. If there is friction, the solution is entirely different. If the chute is frictionless, that curve is a cycloid between these 2 points. Okay, what is a cycloid? When a circle rolls on a straight line without slip. Okay, you have studied this thing a lot of times. So any point on the circumference will, you know, create a curve like this, which is a cycloid. So say cycloid, I mean the curve similar to that type of a cycloid is going to be the solution. Okay, I would suggest for the solution of Brachistochrone problem, you need to go and see some YouTube videos. Okay, and actually, if I recall correctly, in the Birla Museum, there is one setup which demonstrates that, you know, the rectilinear path is actually taking higher time than that, you know, the Brachistochrone path. Okay, so that is also there. But you can, for the time being, you can see some YouTube videos how that cycloidal path gives you the least time. Now, back to your question, if y is the solution and y tilde is not, y tilde is some arbitrary function, but in order for y tilde to be admissible, to be considered for the post of, you know, the minima, the function that minimizes that functional, in order for it to be eligible, it needs to have the same boundary condition, okay, that as y. Okay, now while we were solving Brachistochrone problem, the value of y was given at both the ends, so it must satisfy on both the ends. Okay, now if y tilde is any arbitrary function which satisfies the boundary condition, and y is the actual solution of that minimization problem, okay, the difference between the two is actually the variation delta y. And actually what you can do is you can multiply with a scaling factor. Okay, you can get different y tilde by taking epsilon value different, and which also tells you that y tilde equals y when epsilon equals 0. ওকে, এবার ভালো করে ডেরিভেশনটা আগের দিনে দেখো, তার থেকেও বেশি করে আগের দিনের লেকচারটা 2-3 বার প্লে করে দেখো, তাহলে কিছুটা ক্লিয়ার হবে। এর পরের অংশটার জন্য ভিডিওটা ভালো করে দেখো কিভাবে আমরা মিনিমাইজেশনটা করলাম। ওকে,
হ্যাঁ,
আর কোনো কোশ্চেন না থাকলে আমরা এখানে শেষ করছি।
হ্যালো স্যার।
হ্যাঁ বলো।
স্যার বলছিলাম যে ব্র্যাকেস্টোন প্রবলেম যেটা আছে ওইখানটাতে মানে সলিউশনটা হচ্ছে তো বেসিক্যালি ওই মানে সাইক্লয়েডের যে মানে ফর্মটা যেটা পাচ্ছি ওইটা হচ্ছে।
তোমার কোশ্চেনটা ঠিক ক্লিয়ার হলো না, আর আওয়াজটা একটু আস্তে আসছে।
ও স্যার বলছিলাম যে ওখানে যে সাইক্লয়েডের যে ফর্মুলাস গুলো মানে ওখানে যে ডেরিভেশনটা আছে সেটা হচ্ছে সলিউশনটা ব্র্যাকেস্টোন প্রবলেম।
না, দুটো পার্ট আছে। একটা হচ্ছে তোমাকে প্রথমে আমার মনে হয় ক্লাস 4 এর মধ্যে এরকম ভাবেই আছে, ইনিশিয়ালি there is a derivation, okay, যেভাবে আমরা আগের দিন পড়লাম, to arrive at the the expression for the Brachistochrone problem. Every problem has a mathematical expression, mathematical statement, সেই ফর্মটাতে পৌঁছানো, ঠিক আছে? So that we have already done for the Brachistochrone problem. That is so for your assignment, I mean, obviously you will be writing that for Brachistochrone problem as well, but the additional task for you would be regarding writing the problem statement would be only for isoperimetric and geodesic problem. Now the solution part has not been done for any of the problems. Okay, so that is going to be new. এবার যেই আমরা Brachistochrone problem স্টেটমেন্টটা লিখলাম, even after that we were not at that point when we wrote Brachistochrone problem, okay, we were not in a position to solve that one. So then we learned how to get the differential equation when you have to minimize a function, hence Euler Lagrange equation. Okay, and now using Euler Lagrange equation you can write only the governing differential equation of the Brachistochrone problem. So there is a functional statement, then differential equation statement, and once you solve the differential equation, then you have the solution. Then you have the functional form of y. That's the solution. Okay, so that part has not been done for either of the problems. Okay, বুঝা গেল?
হ্যাঁ স্যার, কারণ হচ্ছে আগের দিন আপনি প্রবলেমটা দিয়েছিলেন অ্যাসাইনমেন্ট হিসাবে, তো এটা করা হয়েছিল কিন্তু এটাতে সাইক্লয়েড ওটা আসেনি, কিন্তু এটা করে রাখা হয়েছিল, ওইটা আমি বুঝতে পারছিলাম সাইক্লয়েডেরটা মানে অ্যাকচুয়াল কি ওটা সলিউশন কিনা।
আচ্ছা, মানে নোটস সলিউশন খুঁজে পাওনি বলছো?
না স্যার, নোটসের সলিউশন পেয়েছিলাম, আমাদের কিছু ভিডিও স্যার ছিলেন ওইটা সাইক্লয়েডের ছিলাম, কিন্তু আমি বুঝতে পারছিলাম না যে মানে একটা সলিউশন না সলিউশন, ওইটাতে পুরো মানে যেটা আগের দিন করা হয়েছিল সেটাতে খালি ডেরিভেশনটা ছিল, মানে ওইটা ডিরাইভ করা হয়েছিল, ওই জন্য একটু প্রবলেম হচ্ছিল বুঝতে। ও মানে এই প্রবলেম মানে ব্র্যাকেস্টোকনের সাইক্লয়েড ফর্মুলাটাই হচ্ছে মানে অ্যাকচুয়াল সলিউশনটা।
হ্যাঁ, Brachistochrone প্রবলেম সলভ করলে যে প্রোফাইলটা পাওয়া যায় দ্যাট ইজ এ সাইক্লয়েডাল প্রোফাইল, ঠিক আছে? দ্যাট মিন্স it would be a combination of sinusoidal plus linear function, ঠিক আছে? তো সেটা দেখো, আমার ধারণা আমার নোটে যদি নাও থাকে, সিএস যোগের নোটে ডেফিনেটলি থাকবে এই ডেরিভেশনটা। আর বাকি প্রবলেমগুলোর জন্য প্রবলেম স্টেটমেন্টটাও করানো হয়নি, ঠিক আছে? এবং বাকি প্রবলেমগুলোর জন্য ওই constraint problem হলে কি বিশেষ the special treatment that you require for constraint problems, that also has not been discussed. Okay, so all of those just for the timing is your assignment, okay, only to make you do more and more problems involving variational method. Okay, you can go through if it is not available in my note. I guess it should be. If it is not, then you can go to Chandrasekhar Joke's classroom and uh, try to understand it and try to derive it.
Okay, sir.
Okay. Any other queries?
So, you
Yes.
told that you will discuss about strong form.
Huh.
If you can please tell in short that what is strong form. Mean
Okay.
um, for
I'll
a
tell you what is strong form and what is weak form. Okay. I have
okay.
actually told you already, but I'll
uh,
tell it again. But I'll not tell you why something is strong, why something is weak. That is reserved for next day's class.
Okay.
A differential equation. So
Mm.
we have seen that the problem can be written in three different forms. One is that minimization of the potential energy.
Okay.
And I'm talking about an equilibrium problem. Okay. If it is not a problem in mechanics, if it is not a problem of equilibrium, it is going to be a different type of equation, but it will still be a functional. Okay. For example, in Brackett's problem, it's not some kind of potential energy, but it's a functional. But for it was time actually in Brackett's problem. But for this problem, deflection of a bar, it is an equilibrium problem, and hence what we are minimizing, that functional, is essentially a potential energy. So that is that statement. Okay, that integral statement is our aim statement. Okay, so that is one type of weak form. When we take the first variation, we get the variational form, okay, of the same equation. Okay, and that is our V statement or variational statement. That is also another weak form. Now, the third form, okay, what we have seen that this flow from M statement to V statement is we have done twice. One for the Brackett's problem, one for the general functional, and other one for this bar problem. We have done this. So going from M statement to V statement, we have done, and going from V statement to Euler Lagrange equation or differential equation also we have done. Okay. Now this differential equation along with the boundary conditions, okay, you saw that, right? That Neumann boundary condition as well as the differential equation both were the outputs of the V statement, right? Both we could obtain from the V statement, uh, the differential equation as well as the Neumann boundary condition, the boundary condition on the stress. So we could get both of those. Only thing we required as an input was the that thing, your Dirichlet boundary condition. So this third form, this with the differential equation and the boundary conditions, okay, both of which could be obtained from the V statement, is your strong form. Okay.
Okay, sir.
Okay.
Okay, sir.
Hello.
Huh, bolo?
Hi, sir. In today's class, we have introduced that the function is consisted of u and u bar. So now we are introducing a variation of u, that is v. So we are introducing this arbitrary variation because the endpoint, the boundary condition is not fixed. Like in Brackett's problem, we have x1, x2, y1, y2.
No, even in
And
Brackett's problem, we introduced the variation, right? The delta y was the variation. Okay. So there was y and y tilde. Okay. Y tilde is some arbitrary uh, function. Okay. And y is supposed to be the function that minimizes some functional. Now, if y tilde is arbitrary, but still admissible, or still, is a candidate for solution, in order for it to be a candidate for solution, it must satisfy all the boundary conditions on y, right? So if you take all the functions that satisfy the boundary conditions that are given, okay, for example, y at x1 is y1, y at x2 is y2. All the functions that satisfy those boundary conditions are not necessarily the solution to that optimization problem. That means Not all such functions minimize that functional. Only one of them does. The other ones would be slightly off from that function. Okay, মানে ধনুকের ছিলার মতো হচ্ছে যে দুটো, that there would be a gap between the two, connected at two ends, but there would be a gap in between. So this gap is what we are calling as variation. Okay, and by definition variation has to be zero wherever the value of u is given or the value of the function is given. ঠিক আছে, তুমি আগের দিনের ভিডিওটা চালিয়ে দেখো, আজকের লেকচারটা চালিয়ে দেখো, we have done the equal treatment in either situation. এই আগের দিনের ভিডিওটা কেউ ডিলিট করে দিচ্ছে জানো?
হ্যাঁ স্যার, ডিলিট হয়ে গেছে।
কেউ করো না কিন্তু, এরকম নিজেদের ডাউনলোড করতে হয় করো, কিন্তু ভিডিওগুলো ডিলিট করো না, ভিডিও বা স্টাডি মেটেরিয়াল যেই করে থাকো করো না প্লিজ। Any other queries?
No, sir.
Okay. So we'll meet on Wednesday.
স্যার নেক্সট ক্লাস কি তাহলে বুধবারে?
হ্যাঁ বুধবার।
আচ্ছা
বুধবার কি আমরা
আচ্ছা
ক্লাসটা 9টা থেকে করতে পারি?
সকাল?
অবশ্যই সকাল, তোমাদের সকাল 10টায় ক্লাস, কিন্তু আমার পক্ষে 9টায় করলে যেটা সুবিধে যে আমি তারপরে কলেজে যেতে পারি।
ওকে
স্যার 9টা থেকে নেবেন স্যার।
ওকে স্যার।
কারো অসুবিধা আছে?
নো স্যার।
No, sir.
ভালোই
নো
হবে।
স্যার।
ওকে।